We discussed before that the activation function, that function that takes you from the input to the output for a perceptron, is the step function or the Heaviside function. And that comes with certain limitations. So let's talk about those limitations and how we might modify the activation function. So here is our perceptron network, which we were talking about earlier. Ultimately, what we want to do is to find the weights and biases of this network to solve the problem that we are trying to solve, the vision task. So in that context, what we need to do is to be able to see what the impact of changing a particular parameter here. All these weights and biases, we can call them parameters of the network. So if you take any one of them, let's say this weight right here, what we want to be able to say is if we change this weight, what is the impact on the output A? So if you change the weight by delta W, we expect a change in the output of delta A, and this could be towards the desired output or away from it, but we'd like to be able to measure it. In other words, ideally what we want is that a small change in a weight or a bias leads to a small change in the activation of the output towards the desired activation. Well, in this context, we have a certain problem with the perceptron and the way it's designed. And the problem is that we know that the activation function for a perceptron is the step function. So let's say that we actually want to see what the impact on the output A is going to be if we change the weight W1. So we have, in this particular case, Z, which is again Wx plus B. So if you change W1, that's going to change Z, and that is going to have an impact on the output A. So let's say that we change W1 by delta W1. And as a result of that, Z changes like so. But we see that the activation does not change. It was 0 before, but because Z is less than 0 and continues to be less than 0, the output remains completely unchanged. It's 0. Now let's say you go the other way, and it turns out that you haven't changed W1 enough so that Z doesn't change substantially, and therefore the output continues to be 0. So in some ways what I'm saying is you've changed W1 both ways, and yet you've learned nothing about the impact of W1. If you change it further, interesting thing happens. All of a sudden Z is positive and the activation flips to a 1. It goes all the way to a 1, from a 0 to 1. So therefore you have the makings of a fairly unstable system. It's very difficult to figure out how to adjust the weights and the bias in order to get to the desired activation or the output because of the lack of change or the sudden change in the output with a small change in the parameters. And this is even more the case when you have a network of perceptrons. A typical network could have 1 million perceptrons. That's millions of weights and biases. So the point that I'm trying to make here is that it's difficult to deal with a network where the activation function is something as dramatic as a step function. We would like to be working with smoother functions. So that brings us to the sigmoid neuron. In the case of the sigmoid neuron, which is exactly like the perceptron, the activation function, which you apply on Z, is now called sigma, and that function is no longer a step function, but the sigmoid. The sigmoid is 1 over 1 plus e to the power of Z. And if you take a look at that activation function, it looks like a blurred version of the step function. You see that right here. And now the behavior is a little bit more benign and predictable in that if you change the parameter W1, and let's say Z moves in this direction, you have a measurable change in the negative direction, in the opposite direction in the output A. If you go the other way, you see that the activation increases, again in a measurable way. And if you further increase it, you see that it increases further, and so on. In other words, the output transitions more smoothly with respect to changes in the weights and biases.